Hi everyone. So in this reaction we're going to do a Fischer esterification reaction. So we're going to start with a carboxylic acid, acetic acid, powdered vinegar, and we're going to react it with isopropanol, rubbing alcohol. And this is a reversible reaction, and what we're going to make is isopropyl acetate, an ester, and water is the byproduct. So if we look at this reaction, this part of this molecule is this part of the ester. The alcohol, with the exception of the H, is this part of the ester. And the water is this OH and this H, which is here. And we're going to use the catalyst H2SO4 to drive this reaction. So in the actual reaction, we're going to use 7 milliliters of the acetic acid and 3.5 milliliters of the isopropanol. And basically, that means what we're going to find out in a second when I do the limiting reagent and the theoretical yield is that we're using the acetic acid in excess. Because this is a reversible reaction, by Le Chatelier's principle, adding more of one of the reactants drives the reaction towards the product. So in this case, we're going to use the acetic acid in excess because, as you're going to see when we do the separation scheme, it's relatively easy to remove this from the reaction mixture by adding sodium bicarbonate. So in actuality, these are the volumes that we're going to use. And I'm going to label this one acetic acid, this one isopropanol, and this one isopropyl acetate, so I don't have to write the words out every single time. In my example calculations, I'm going to use 2.6 milliliters of the isopropanol and 7.5 milliliters of the acetic anhydride, just so I get different numbers. So this is the actual, this is the example. So I'm going to start with the acetic acid just because it's first. I'm going to convert from milliliters of acetic acid to grams of acetic acid using the density, to moles of acetic acid using the molar mass, to moles of isopropyl acetate using the balanced chemical equation, and then grams of isopropyl acetate, again using the molar mass. So this is my plan of attack. I'm going to do this exact same plan of attack, substituting in isopropanol in each case for the isopropanol. So in this case, if I start with 7.5 milliliters of acetic acid, I want to convert it to grams using the density. Well, it turns out that the density is 1 milliliter of acetic acid is 1.05 grams of acetic acid. Now I want to convert it to moles of acetic acid using the molar mass. And it turns out that the molar mass of acetic acid is 60.05 grams of acetic acid is 1 mole of acetic acid. Now I want to convert it to moles of isopropyl acetate using the balanced chemical equation, and they're all 1 to 1. So it's 1 mole of acetic acid gives me 1 mole of isopropyl acetate. And then finally to grams of isopropyl acetate using the molar mass of isopropyl acetate. So 1 mole of isopropyl acetate is 102.13 grams of isopropyl acetate. And when I do all that math, I find that we make 13, to two significant figures, grams of isopropyl acetate. So if I use all of my acetic acid, I'll make 13 grams of isopropyl acetate. I want to repeat this entire procedure, same exact thing, for the isopropanol. So starting with, in the example, 2.6 milliliters of isopropanol, I want to use the density to convert it to milliliters. And it turns out here 1 milliliter of isopropanol is 0.785 grams of isopropanol. Now I want to convert it to moles. Well, it turns out that 1 mole of isopropanol is 60.10 grams of isopropanol. Now I want to convert it to moles of isopropyl acetate. Everything's 1 to 1. So 1 mole of isopropanol for 1 mole of isopropyl acetate times, molar mass is the same, so I want to convert it to using the same conversion, 1 mole of isopropyl acetate per 102.13 grams of isopropyl acetate. And I'm doing this relatively quickly because We did this in Gen Chem, we did it in previous experiments, so I'm not spending a lot of time on it. And what we end up with here is 3.5 grams of isopropyl acetate. This means that isopropanol is the limiting reagent, and the theoretical yield, based on my numbers, the made-up numbers, is 3.5 grams. You're going to want to do this for the actual numbers and figure it out yourself. You're going to get the same limiting reagent, but you are going to get a different theoretical yield. So we use one reactant in excess to drive the reactant to the products because it's reversible. Now that we have an idea of what we're doing, like what we're mixing together and how much of it, let's look at the mechanism of this reaction, what's actually going on. So in this mechanism, the first thing we have is we have acetic acid, which looks like this, and it's in the presence of H2SO4 or H+. Now, in order to get the product, right, we need this oxygen to end up attacking this carbon. But before this oxygen can attack this carbon, we want to add a proton to this. So in this case, this oxygen attacks this proton. This oxygen acts as a nucleophile, the H+ acts as an electrophile, and what you end up with is CH3, C, double bond O. Now it has one lone pair and a bond to an H and a plus charge. And we end up with an oxygen and a hydrogen. And it turns out that there's 3 resonance forms of this, because we can move these electrons up there and get CH3, C, bond OH. Now we have the electrons up here. Bond, well, let me keep it in the same spot. Bond OH, like that, and now the plus charge is on the carbon. And I'm running out of space here, but I'm going to try to cram this in here. We can end up with CH3, C, where these electrons come here, double bond O, bond H with a plus charge, bond O, bond H like this. So we end up with 3 resonance forms. Now the resonance form that we want to show being attacked is this one with the plus, but of course in a resonance, all 3 of these exist at the same time. It's not like sometimes it's this one and sometimes it's this one and sometimes it's this one. It's the resonance hybrid of all 3. So we want something to attack this. Well, what do we have? We have an alcohol. Specifically, I'm not going to try to draw the carbons, I'm just going to draw it like that. So this alcohol can then attack here. Here, the electrons on the oxygen act as a nucleophile, and they attack this carbocation, which acts as the electrophile. And what we end up with is, I'm going to write it over here, CH3, bond C, bond OH, bond OH. So they just go along for the ride, these 2 OHs. And we end up with this new bond to an oxygen bonded to the alcohol, like so. So in the first 2 steps, I identified the nucleophile and the electrophile. So here the oxygen acted as the lone pair on oxygen acted as the nucleophile, and the H+ acted as the electrophile. Here the carbocation was the electrophile, and the lone pair on this oxygen was the nucleophile. I'm going to stop doing that, but when you're writing your mechanism discussion, you should identify them in each step. The next thing we're going to do is we're going to look at this, and this has a positive charge on it because it has 1, 2, 3 bonds and a lone pair. So we want to get rid of that positive charge. Well, we have water in the solution, so water can grab this proton, and these can come here. And what we end up with is CH3, bond C, bond OH, bond OH, bond O, plus H3O plus as a byproduct. So in this case, we don't have any charges, which at first glance looks good, but what we need to realize is that even though we don't have any charges, we have 3 oxygens bonded to a single carbon, and these are all electron withdrawing groups, and that's not particularly stable. So what we're going to end up with next is basically a dehydration of this ester hydrate, if you will. In including this. So what we're going to do is we're going to protonate one of these oxygens in a similar way to what we protonated in the original case. And what we end up with is CH3 bond C bond OH with its two lone pairs, bond O. Now it has an extra H attached. I guess I drew it on the top and then drew it on the bottom, but it's the same thing. Plus charge, bond, oxygen, like that. So that's what we end up with in our reaction. Now, this has three resonance forms. Sorry, not this one. So, next thing what we're going to do is we're going to kick out water, which is a good leaving group. To do that, these electrons come down and water leaves. And what we end up with is CH3 bond C, double bond O, bond H with a plus charge, bond O with two lone pairs, like this. And this one now has the three resonance forms that are very similar to the resonance forms up here. I'm not going to draw them, but I would suggest you draw them for practice. Now we have this plus on this oxygen, and we have water in the solution, both because it's a product of this part of the reaction and because it's just in solution. So what we're going to do is we're going to remove this proton. So this comes along, grabs this goes in here, and finally what we end up with is CH3 bond C, double bond O, no more H, bond O, and it's the ester, plus H3O plus. So we have now gone from our starting materials, a carboxylic acid and an alcohol, and ultimately we have formed the ester. So this is the mechanism of the reaction. Make sure that when you're writing the mechanism discussion, one, think about the resonance forms that are here, and another, which are the same as this one, essentially. And then another thing to think about is what is the nucleophile and what is the electrophile in each step. And if you go back in the video, we talk about it for the first two steps, and you can identify it in a similar way for the other steps. So that is the mechanism of this reaction. So next I want to talk a little bit about how we're actually going to do the reaction. So what we're going to do is we're going to start with acetic acid, isopropanol, and sulfuric acid. And specifically, we're going to start with 3.5 milliliters of the isopropanol, 7 milliliters of the acetic acid, and around 1 milliliter of the concentrated sulfuric acid. We're going to put that into a round bottom flask, and then we're going to reflux it. Remember that when we reflux it, we have to be careful to do a few things. First of all, we want cold water here and hot, cold water going in here and then coming out here. And then we want this extractor arm basically a bit up here, and we're going to use a heating mantle to heat this. So we're going to gently boil this solution, and as it comes up into the condenser, this is going to be cold and it's going to fall back into solution. So we're going to reflux it. And we're going to reflux it for about 45 minutes. Then after the reflux, we're going to do an extraction. And to me, one of the best ways to talk about an extraction is in terms of the separation scheme. Now, this is the last separation scheme that I am going to do completely for you on paper. I will talk about them in future videos, but I'm not going to show the exact separation scheme anymore. What I strongly recommend you do is think about where we're starting from the separation scheme, which we'll talk about in just a second. And after we've talked about what we're starting with, think about how you're separating these things. One good thing to do is to look at the experimental procedure as you're getting started. As you do this more and more, you're not even going to need the experimental procedure in order to do this. So what are we starting with in the reaction mixture? Well, we're going to have in the reaction mixture our product, because the separation is separating our product from everything else. Our product in this case is isopropyl acetate. What else are we going to have in there? Well, we're going to have sulfuric acid, because we use that. We're going to have acetic acid, because the limiting reagent is going to be the isopropanol. We're going to have water, and we're going to have trace of the isopropanol, because It may or may not all get used up. It's a reversible reaction, so it probably isn't all going to get used up. Sorry, I didn't realize I didn't have the reaction on the screen. So we have the isopropyl acetate, the product. We have the sulfuric acid, the acetic acid. We have water, a product of the reaction. And then we have traces of isopropanol because it is a reversible reaction. So the next thing is we are going to add two 6 milliliter portions of water and two 8 milliliter portions of diethyl ether. So we're essentially going to add water and ether, and we're going to have two layers. We're going to have an aqueous layer, which implies there's water present, so I'm not going to write water every time. And the aqueous layer is going to have some stuff. Now here's where I suggest you stop. I suggest you stop the video and complete the separation scheme and then watch the video. You don't have to, but that's what I suggest you do because I'm not going to be going over these again in the future. So what are we going to have in the aqueous layer? Well, the aqueous layer should have our sulfuric acid, our acetic acid, water, of course, it's the aqueous layer. And I'm going to put the trace isopropanol over here. This is a hard one because it could be in both layers. So then what do we put over here? Even more trace isopropanol. We're not really going to do anything to get rid of the excess isopropanol with the possible exception of distillation at the end, but I'm not going to bother with that. So we have these things. In our ether layer, or our organic layer, we're going to have isopropyl acetate, our product, ether, but we're also going to have traces of our acids and traces of water. So we're going to have trace sulfuric acid, trace acetic acid, and trace water. How are we going to get rid of these acids? Well, these acids are somewhat soluble, very slightly soluble in the organic layer. The acetic acid is an organic acid, so it might have a little more solubility in the organic layer. There's also traces of water in the organic layer, which can dissolve the acids. So basically, we want to get rid of these acids. Well, what do we use to do that? We use a base. And in this case, we're going to use 5% NaHCO3, sodium bicarbonate, which is of course 95% water. So we're going to end up with an aqueous layer and an organic layer. The sulfuric acid and acetic acid will become sodium sulfate because they'll react, and sodium acetate. These are ionic compounds which have zero solubility in ether. So these are completely insoluble in ether, so they are removed from the organic layer. That's important. That's why we add this base. As always, when you're adding sodium bicarbonate, the byproduct is carbon dioxide. It's very important that you've gotten most of the acids out of there because you don't want to add this to a closed container with lots of sulfuric and acetic acid. You'll generate a lot of CO2. Usually the top will pop off, which is not good because stuff can come flying out of there. And occasionally the glass will actually break. So make sure you've thoroughly washed out your sulfuric and acetic acid with water before adding this 5% sodium bicarbonate. Another way of checking this is if you start to see lots of bubbling, then you need to stop and open your flask quickly in order to release the pressure. All right, so now we've got these two things, sodium sulfate and sodium acetate. In the organic layer, we of course still have our isopropyl acetate, our ether, and our traces of water. So we've done this a bunch of times. To get rid of the traces of water, we add anhydrous Na2SO4. And we get a solid, which is Na2SO4 and some number of water molecules. And we end up with an organic, which is going to be our isopropyl acetate and our ether. Then we're going to finally distill, and I'll talk about that more in just a minute. And basically when we distill this, we're going to get fraction 1 and fraction 2. Our first fraction should contain ether because it's a lower boiling point, and our second fraction should contain isopropyl acetate because it's a higher boiling point. So this is essentially what we're going to do. The next thing that I want to talk about a little bit is distillation. So you may recall from last semester that we set up this distillation apparatus. So you're going to put your mixture, after you do the separatory funnel that we just talked about, you're going to put your organic layer in here, and then you're going to dry it. Oh, you're going to dry it, then put it in here. Okay, and then you're going to heat this. You have a distillation head. Notice the place of the thermometer, and also notice that you're going to actually want to measure the boiling points. The boiling point of ether is around 35 degrees C, and the boiling point of isopropyl acetate is somewhere around 87 degrees Celsius. Then, after the distillation head, you're going to have a condenser, water in, water out. Then you're going to have a vacuum adapter. Notice that this is open. Okay, we want this to be open. We don't want to heat closed containers. And then you're going to have a receiving flask, and you're going to collect 2 fractions. And it's important that you know the mass of the flask so you can weigh the mass of the fraction. The second fraction is especially important because that's your product. So here's what we're going to do. You're going to take a heating mantle and you're going to heat this up. Ether is going to start to boil. You're going to notice that this temperature goes up to around 35 degrees C, and then you should start to see stuff dripping over here. Note that you want it to drip fairly slowly. You don't want it to be dripping really, really fast. Then what should happen, in theory, is this temperature should start to drop as the ether is running out. However, in practice, ether has a boiling point only 10 or 15 degrees above room temperature. So we're not going to necessarily see a large temperature drop, but we should see the temperature start to rise again as the isopropyl acetate, which is boiling point somewhere around 87 degrees, starts to boil. Then we want to measure the boiling point of the isopropyl acetate. So boiling point is one way that we are going to monitor what our product is. So simply by reading the thermometer, when your second fraction is dripping, right, so we let the ether boil out, then the temperature will either start to rise and the dripping hopefully will stop for a short time, or in an ideal world it'll go down and then go back up again. Then we should put on this fraction 2, and we should collect most, but not all, of our isopropyl acetate. We don't want to boil to dryness. So in this case, we should then have a boiling point of isopropyl acetate. One of the last things I want to talk about is the IR spectrum. So once you get the receiving flask and you've distilled over your isopropyl acetate, what you want to do is record the IR spectrum. And the possible things that could be in there are acetic acid, isopropanol, and isopropyl acetate, the product. Now, boiling point is going to be a good indicator of whether or not you have isopropyl acetate or not. But another indicator is the IR spectrum. I will note that the boiling point of acetic acid is around 117 degrees C, and the boiling point of isopropanol is around 82 degrees C, which is only a little bit different than the isopropyl acetate. So let's look at acetic acid first. Acetic acid has CH3, C double bond O, bond O, I don't know why I did that, OH, like this. So you can see here clearly, we have an OH, we have a CH from here, and we have a C double bond O. Now let's look at the next one. Let's look at 2-propanol. 2-propanol is CH, CH3, CH3, bond OH. In this case, we have an OH here, we have the CH here, and notice what we don't have. Between 17 and 1800, we have no carbonyl, which makes sense because there's no carbonyl. Now let's look finally at our product. Here's our product. Our product is CH3, bond C, double bond O, CH, CH3, CH3. So we do have the C double bond O, and we also have the CH. What we don't have is no OH. So we can identify the IR of our product as not being our starting material because we have the presence of the C double bond O and the lack of the OH. Also, a good reason it's not acetic acid is one, because we worked it up with sodium bicarbonate, so if we did that properly, it's pretty much impossible. Or the other reason is the boiling point of this is very, very far different from the boiling point of our actual product, but you can also identify it by the IR as well. Note that the way we made this, including the distillation, we didn't recently interact it with a protic solvent. The lack of OH is a pretty good indicator that the molecule has been converted, and it's also fairly likely to occur because we're not going to have other sources of OH readily available to contaminate our results. So the final thing that I would like to do very briefly is talk about the hypothesis. And the hypothesis that's in your syllabus says, focus on the type of reaction used to form isopropyl acetate, so a Fischer esterification. The method of separation, which is distillation, which separates things based on their boiling point, so the ether boils out first and the isopropyl acetate second, due to the differences in their boiling point, and how the product will be identified among the fractions collected. In this case, we're going to identify it by boiling point, and we're going to confirm that our suspicions by doing an IR spectrum and determining that it is no longer isopropanol. Also acetic acid, but the boiling point is so different there that you're probably not going to see have a question of which one it is based on the boiling point. Between isopropanol and isopropyl acetate, the boiling point is only 4 or 5 degrees different, so there's a little bit of a question. Acetic acid, is well over 100, so there's not much question there. I hope that you enjoyed this video. Again, I'm no longer going to be going over the separation schemes in this kind of detail. I will talk about them generally, but I will not be writing them out anymore. So thanks for watching.